Hello, my name is Mrs. Jane Owen from Penglai School, and I'm here to do some revision on specified practicals for Unit 2. I'll be looking at the electricity and photons experiments, and if you look in your practical booklet, this is practical 7 to 10 and the last one 16. So I'll leave the waves one for another revision session. Okay, let's share my screen with you. Okay, so first of all, let's have a look at experiment 7. So the current voltage characteristics of a bulb and a wire. So if you have got the WJEC lab book, this is the page from that. And for this first experiment, you just set up a simple circuit with a variable power supply so that you can do a range of currents and voltages through a component. And we're going to do two components, a bulb and a wire. As you can see here, we've got a set of results, and we've plotted those results, current against voltage. Now, just let's have a little look at how this particular candidate has set out these results. They've measured the voltage and they've stated that the voltage is plus or minus 0.01 of a volt. However, all of their results are written to plus or minus 0.1 volt. So there's a discrepancy here between the resolution of the voltmeter that they've used and what they've written down. So I suspect here, because all of the results are to the nearest 0.1 volt and there's nothing that's deviated from that, I suspect that they are actually to plus or minus 0.1 volt, and that's how it should be written at the top. So whatever your resolution of your apparatus is, you write it down, the results accordingly. Now, with the current, they've got plus or minus 0.1 amp. And actually, all of those are consistent with what they have actually got. So that looks correct. And they've done the same thing for the voltage for the bulb. So it should be 0.1 of a volt. Okay, so let's have a look at the graph. So they've plotted current against the voltage. They've forgotten to label the voltage on the axes. So remember, when you plot a graph, to remember the units for WJC as well as the label heading. And then they've plotted the graphs, and then they've drawn a line of best fit. And you can see for a bulb, it is a non-linear characteristic of current against voltage. So we say current against voltage characteristics. We always put current on the vertical axis and voltage on the horizontal. And a nice curved trend like that suggests that it is, in fact, a bulb. Whereas if we have a straight line through the origin, this is characteristic of a resistor or a resistance wire. So a straight line going through the origin. It doesn't matter how steep it is, as long as it's a straight line going through the origin, then we can say that the current is proportional to the voltage and that this obeys Ohm's law. Ohm's law being that the resistance is equal to the voltage divided by current. So provided we haven't changed the temperature or changed the wire at all in any way, or the resistor at all, then the ratio of voltage to current will be the same, and it will be the same everywhere along that wire. Now, strictly speaking, to find the resistance, we find the resistance at a particular point and not the whole gradient of the graph, or the inverse gradient of the graph, as it would be here, because it's the change in current over the change in voltage. What we tend to do with resistance is work out what the voltage divided by the current at that one point, and then we take another point on the line, and we take another point on the line, and you'll see that every single time the resistance is the same, the voltage divided by current will be exactly the same. Whereas if you did it along with the bulb, you'd find that actually the resistance would increase, so that the resistance equals voltage divided by current. And this is something to do with that in the bulb at higher voltages, the temperature increases of the wire inside the bulb, and so that provides more resistance for the electrons flowing through the vibrating atoms. Okay, so that's the first experiment. And I think you can see that this candidate has done a gradient, and that they've then inverted the gradient to get the resistance. This is not conventional, but it will come up with exactly the same value as if we did it as a point in the case of the resistance wire. It's just a point to note that Ohm's law is the ratio of the voltage to the current. Okay, let's move on. Experiment 8. This is about the resistivity of a wire. Resistivity is given by rho, and rho equals RA over L. The resistivity is a constant for that particular material, and this experiment is also part of Unit 2.2. And the resistivity takes into account the resistance as well as the dimensions of the material, and that's why it provides a constant for that particular material, so that you can compare resistivities of different materials and different alloys. Okay, so if we rearrange this, what we do in this experiment, we set up the standard circuit of an ammeter in series, a voltmeter in parallel, and we're doing it across a resistance wire, nichrome or constantan. We're doing this and we're going to vary the length of the wire, and we're going to measure the resistance of the wire, and we measure the resistance of the wire by doing voltage divided by the current from the voltmeter and the ammeter. So we're not measuring the resistance directly, we're measuring the voltage, measuring the current, and we calculate the resistance. So let's just kind of like rearrange this so that we get resistance on its own, because I think what we are going to plot, we're going to plot resistance against length in the end. So R, let's isolate R, take everything else away, rho L over A. Okay, let's swap it around so that we've got R equals rho L over A. Now we want to relate that to Y equals mx. I'm going to put plus C in brackets, but the C here will be equal to, or should be close to, 0, because there isn't a intercept there at all. So I'm just going to assume it's a Y equals mx graph. But again, I'm not going to, if you've seen any previous recordings, I'm not going to force it through the origin here. It might be close to the origin, but I'm not going to force it. So Y is going to be plotted on the vertical axis, which is going to be the resistance. X is going to be the horizontal axis at the bottom, and that's going to be the length. And so the gradient M gives us, if I put that down here to be consistent with the graph when we see it, the gradient M is equal to the resistivity divided by the cross-sectional area. And I've just taken that from this equation here, okay? So all I've got to do then is plot a graph of resistance against length. Remember, I've got to convert the length into meters, so that if my cross-sectional area is in meters squared, then I can get resistivity in ohm meter. So M gradient times by cross-sectional area will give us the resistivity. Now let's have a look at this candidate's results. they have quite sensibly checked out the diameter of the wire in several places. I probably wouldn't have done it every 10 centimeters. I probably would have done it at the beginning, at the end, and in the middle, just to get 3 readings and take a repeat. But this candidate's done 10. And that's fine. And they've got a value for the diameter. So this actually represents the diameter, even though it's not labeled as such. Let's see if I can diameter, add that in there. And then what we do to that diameter then is halve it, divide it by 2 to get the radius equals diameter over 2, and then put it into pi r squared to give the cross-sectional area of the wire that you are testing the resistance of. Okay, so once you've done, make sure that you have converted from, so this would be in millimeters. I just want to see if that candidate has done 10 to the minus 3. Yes, they have. So this will be probably most likely in millimeters. So we ought to put D in millimeters at the top. Notice this candidate hasn't done the headings on the units at all. And this would be, that's times 10 to the minus 3, so that you've got the area then in meter squared when they calculate it. Okay, so once we've got that area, we can get our gradient from the graph here. So if we just do a quick triangle, I'm just thinking, can I do the triangle? I'll come down from here. Use a ruler. You do use a ruler here. So the gradient m is dy by dx. Make sure you use a very big triangle. 6.6. Take 0 because it goes down to the origin. That's 0. That's 0. You ought to mark, you know, if it is 0. We don't tend to do squiggly lines. You'll see one later on. And you can read that off the whole graph grid. Whether it's 0 or not, you can still label it up. It doesn't have to show 0 at that point. Okay, and 1.2. So this mark here will be 1.2 because every 5 is 0.1. So no, 1.02. Because it's 0.2 between 10 squares, 0.1 between 5 squares, so 0.02 of 1 square. So very, very easy to make these mistakes, especially if you're kind of like in an exam situation. Just reading off scales is really tricky. So if I were you, I would kind of like 0.8, 0.9, 1, 0.9, you know, carry on the scale. So that would be 1.2, that would be 1.1, so this one would 1.02. So just add markings to help you. All right, take away 0, and this is already converted into meters. So the gradient there is worked out 6.47. Okay, and I worked out this area up here is equal to, when I squared it, 8.04, and then times by pi, divided by 2 to get the radius from the diameter, times 10 to the minus 8 meters squared. So take that then. So rho is equal to 6.47 times by 8.04 times 10 to the minus 8, all right, equals 5.2 times 10 to the minus 7 ohm meter. Okay, that looks pretty consistent with what the resistivity of the metal should be. But if you know the wire and you've been told it's nichrome, you can go and look it up in a data book to see how close that is. Okay, all right, so moving on, we've done 2 out of an ambitious 5 experiments here. Experiment 9, variation of resistance with temperature of a wire. Now this time notice that you are setting up an electrical circuit, but we're not using a power supply. All we're doing is across the actual device of the wire, the copper coil, we're just putting an ohm meter across it. If you're putting an ohm meter across a device, you don't need a power supply in with it. So you don't need an ammeter, you don't need a voltmeter. It's all worked out for you on the resistance ohm meter. All right, it's going to measure the resistance straight away. And if you add ice, you can get the cold temperature. If you add hot water, with a kettle, you can get the higher temperatures. So you can do a range of temperatures here and just measure the resistance of that wire. And notice this candidate here has got a set of nice readings. They can only read their resolution of their temperature scale to the nearest 1 degree. We haven't got any more accurate thermometers, so that's what we chose. Of course, if you use the digital thermometer, you could probably go 0.1 degree C resolution, but we just use the standard ones. But notice that it hasn't been ruled off into a table. It hasn't been surrounded by pencil, kind of like straight lines. But the column headings has been included, but we need to separate the unit from the quantity. And we can do this in one of two ways. Either we bracket the unit, or we can put a dividing line between the quantity and the unit. The resistance here is the resolution is plus or minus 0.1 of an ohm. Okay, so these resolutions, it's worth putting them down there because you might have to kind of like work out uncertainties in the experiment later on. So if you can understand what resolution is, how what's the greatest detail that you can measure a quantity to, what's that smallest possible reading that it can pick up, then that gives you kind of like a good basis to kind of work next year more on uncertainties. You do need to do uncertainties here. Okay, and the uncertainties here would probably be the resolution divided by the smallest reading times by 100%. So the resolution will double up as the uncertainty for that particular quantity. Okay, so this candidate has plotted resistance against temperature. I'll move it along a little bit. Can I do that? Yes. Okay. And now notice that this candidate has done that squiggle line here. Now, we don't conventionally do this in physics. I know you can do it in maths and other subjects, but in physics, we tend to be able to read off the whole graph grid available to us. So this actually should have a number here, 4.9, and we shouldn't really have that bit there at all because we can read it off all. So 20 to 10, and this is 0. So this is, for sake of argument, we can read off the y-intercept at x equals 0. So technically, it's not a false origin in terms of what we might want from this experiment of reading the y-intercept. Yes, it is a false origin because it's not 0, 0. But for our purposes, we're only interested in the x-axis, whether it goes back to 0 or not. And if it doesn't go back to 0, it's not a problem. All you have to do is get a reading that is on the line or get a point that is on the line and put it into y equals mx plus c once you've worked out the gradient of the graph. And you can work out what c, the y-intercept, should be if you haven't got 0 there and you can't read it off. Okay, so everything else is looking good. It should be a straight line, all right? Now, how do we know whether it goes to the origin? Well, we've only done it temperature in degrees C. Perhaps it would be a different story if it was temperature in Kelvin. Okay, I'll leave that with you because resistance is all to do with the vibrations of the atoms and the resistance to those electrons flowing through. So if those atoms take up more volume because they're vibrating more, because they're at a higher temperature, then there's clearly a bigger volume for the electrons to kind of like bump in and collide with those atoms, with the electrons of those atoms, and provide a greater resistance to the flow of the free electrons. So as temperature increases, you expect resistance to increase, and in fact, it does it linearly. Okay, right, moving on to experiment 10. Now, determination of the internal resistance of the cell. This relates to the AS Unit 2.3 DC circuits. And there is an equation that we will need for this, okay? Let's have a look. Okay, so we have the voltage provided to the circuit is equal to the EMF of the cell put into the circuit of the battery, the cell. Take away the current in the circuit times by the internal resistance of the cell. Okay, this little r here. Now, if we use a V equals I times by R, as in the R is the resistance of the circuit or in the circuit, all right, whereas little r is the resistance of the cell. All right, this is your EMF supplied to the circuit by the cell. And I is the current in the circuit. And we say that V is the terminal PD. Okay, so if we use V equals IR, we get an expression IR, keeping my R big for the resistance in the circuit, equals E minus IR. And what I'm going to do is I'm going to divide by I because I've got two I's there and I only want one I. So I'm going to have R equals, so divide by I all the way through, E over I minus I over R over I. The I's will cancel, so I'll just get little r. So if I relate that now to Y equals mx plus c, if I plot on my y-axis R in ohms of the circuit, the resistance of the circuit, against x, which is equal to, so y vertically, x horizontally, against, now what will x be? X will be, because it's over divide by I, we say that it's 1 over I. So the units there will be amps to the -1, or you could just put slash amps to mean that it's 1 over. Okay, so that should be a straight line, but you'll notice that the gradient is equal to the EMF of the cell, and the y-intercept, C, is equal to -r. So you expect C to be negative, C being the y-intercept. So you expect it to be like this, where minus C here is equal to -r. So if it's a negative number, for example, -1 equals -r, so r equals 1. And then the gradient of that line would be equal to the EMF of the cell. Okay, so let's have a look at this graph here. All right, I'll expand it a less a little bit. I've plotted, let's just have a look back at the results, see if the results are okay. The internal resistance of the cell. I've got my current, let's put my resolution in, if nothing else, plus or minus 0.01 of an amp. My resistance here, plus or minus 0.1 of an ohm. Notice that they have put their ohms in the body of the table. We don't like this because the whole point of putting our quantities at the top separated by the unit, it means that everything that's in the table has been stripped of its unit, okay? And then we need to work out 1 over current, but quite rightly, they've got the unit there, amps to the -1, because it's 1 over current. You can't get away with this, 1 over amps, 1 over current in amps, because what we want there is a column heading unit that describes the whole column, as it were, not just a part of it. So that wouldn't be any good, but 1 over amps slash 1 over A is fine. 1 over amps slash amps to the -1 will be fine, and 1 over amps brackets amps to the -1 will be fine. But if you find that that -1 is outside the bracket, they won't give it to you unless you've put a dividing line before. You just need a separating mark between the unit and the quantity. Okay, well, they're all pretty consistent because they're all to 2 decimal places. That's fine in keeping with the resolution of the instrument. And just because this has gone to 15 for 3 significant figures, and the first resistance is 2 significant figures, that's okay, because all of them is to 1 decimal place in keeping with the resolution of the ohm meter. But having a look at the current, actually, this is probably good, because 1 over current is a calculated value. Can't put a resolution on that. But what you can do is check for whether they have written it to the right number of significant figures. Now, the current here is 2 significant figures. You don't ignore, you ignore the naught before the decimal point. So we say that that is 2 significant figures. So this one's written to 1 more significant figure, which is acceptable, okay? 3 significant figures. I know WJC like to have it the same, 2 significant figures to 2 significant figures, but it is acceptable to have 1 more. Again, this one's okay. You've got to check row by row. Now, what is not good is that this is 3.3 recurring. So they haven't kind of like put a definitive stop on the number of significant figures they're using. So this, although it looks okay because it's 2 significant figures, if they just written 3.3, that would have been okay. If they put 3.33, that would have been okay. But because they put 3.3 recurring, there's no end to the number of significant figures there. So that actually is not so good. And I know also WJC like it to be consistent down the whole kind of like column. So, but in theory, 2 to 2 is fine. All right. Let's pick another one. So this one is 2 significant figures, quoted 2. Now look, they've given here, well, it's more than just 4 significant figures because they've got a dot there. It's recurring, 705, 705. But anyway, they should really just write it to 3.71 and just, you know, just leave it, say, at 3 significant figures all the way down. So they wouldn't get their mark for the significant figure mark. Even on the next one, all right, you've got 2 significant figures here, and that's jumping to 4 significant figures here. We want 2 to 2 or 2 to 3. And since they started with 2 to 3, it might as well be 3 all the way down, so you are consistent all the way down. Okay, but really the consistency should come just in the raw data, and the number of significant figures related to the raw value of current should hold. Right, moving on. I'm spending too much time on the detail, but it's important because those details are the things that get you the marks. Okay, right. So what we've got here is we've worked out the gradient already. I've looked at, just do your little markings here and right on the graph grid at the top here, 15.5 all the way down to 0. That's my triangle. Draw in a big triangle to work out the gradients, all right? You're not going to get your marks if you go less than half of the length of the drawn line for your hypotenuse of the triangle. So just make it big, all right? I know it comes out at the same number, but you just don't get your marks, all right? You've got to do as big as possible. And then 6 here, and then here, that would be, well, this bit's 1. So 1.3 here. Now notice there's no power of 10s that I need to worry about. So all I have to do is dy divided by dx to get my value of gradient. And that gradient is equal to E, the EMF, 3.3 volts. That seems in tune with the experimental setup. You'd expect 2 cells would be 3 volts. Okay, it's not too far out. Okay, let's move on then to the last experiment of this session. I think we're doing pretty well getting through 5 of these specified practicals that you have to kind of like complete as part of your course. Have a go at doing the graphs. Have a go with, trying to relate y equals mx plus c to these equations, because that's what you will be tested on. You might be given something that is completely different to what you expect, but because you have worked with relating y equals mx plus c to equations in these specified practicals, you'll be able to apply yourself to other situations. And that's a skill, and it's only a skill that you can get by practicing. This is one of my favorite experiments. It's determining Planck's constant using LEDs. It's surprising how close that you can get. Basically, you've got a variable power supply. This is poor here because you can't change one cell, but you can change a power supply with an arrow going through it. Perhaps we ought to have a range of cells here and have an arrow going through it so you can change the number of cells, or you set up a potential divider from one cell. That might be a better way of being able to vary, being able to set this up, because you need to be able to vary the voltage across the LED. And the trick here is you put like an old camera case and drill a hole and put it on top of the LED so that you can change the voltage from a minimum value and catch that point where you just see the colored LED lighting up. And that is what we call the minimum voltage that LED will work. And for different colors of LEDs, you will have different minimum voltages. So from the equation that you have been given, V min equals HC over E lambda. H is Planck's constant. That's what we're trying to find. I hope you get the opportunity to do this in the lab. C is the speed of light. Okay, that's a constant. Okay, 3 times 10 to the 8. E is the charge of an electron, 1.6 times 10 to the minus 19 coulombs. All right, so there are constants there, and there's an equation. And again, you'll notice I'm relating it to y equals mx plus c. All right, hold on, let's just get that back. I want to be able to draw. All right, and notice here, the plus c here, I'm not including it. It's assumed that it will go through the origin. we won't force it through the origin. We'll just say it's a y equals mx graph. So if we plot y v min, don't forget your units, against x, now because it's lambda is over, on the bottom, we go 1 over lambda, so that's meters to the -1. You can write it like that, or you can do 1 over lambda slash m like that, meters to the -1. But yeah, or you can even go like this, 1 over lambda slash meters to the -1 like that. Or you can do 1 over lambda slash 1 over meter. Okay, there's many ways that you can get the mark, all right? But there's many ways equally that the mark will be taken away from you. So therefore the gradient is equal to, this gradient here will equal all of those constants, hc over e. Gradient m. So if we rearrange these, the e goes over to the other side, the c comes under, then we can get an expression for Planck's constant in terms of the gradient. So all we've got to do is times it by e, the electronic charge, and divide it by c, the speed of light, to get the Planck's constant from the gradient. So looking at the graph, okay, that we've got, okay, my points are quite a long way from the line of best fit. Usually when you're doing this experiment, if you do manage to get a camera case on top, you will get those points pretty much on the line of best fit. You'll also notice that there's a big area here where the points haven't been taken. I only did it for the colors that I had. So that would be one improvement, to have more values of 1 over lambda for different colors in between the red and the blue ends, because I've got them all bunched up, like in the middle at the bottom there. Notice I started my graph not at 0 or a squiggly line, but 1.4 all the way up to fit onto the graph grid. And I'm not afraid to start it, not being at 0. I'm not trying to prove whether this goes to the origin or not. What I want from this is as big as gradient as possible, and I want my points to stretch across at least half of the graph grid available. Now, what I do need to watch for this is when I worked out my results here, I've got the wavelength in terms of nanometers, nanos times 10 to the -9 meters. So when I do 1 over lambda, I need to take this into account and do 1 divided by 660 times 10 to the -9, and I get 1.52 times 10 to the 6. So take the powers of 10 at the top to allow for ease of graph drawing. Having said that, put the powers of 10 in there and take account of it when you're having to do your gradient. And do as I've done here, mark out what the redoffs are for the gradient triangle, make the triangle as big as possible, and then get a value for the gradient, taking into account this power of 10 on the bottom on the x-axis. Once I've got that gradient, I can transfer it and I can times it by e, divide it by c to get 7.5 times 10 to the -34 joule second here. It should be, when you look up Planck's constant on the front of your sheet for your all of your equations with the constants on the front that you get for your exam, it should be 6.63 times 10 to the -34. The fact that it's the right order of magnitude, -34, I think is a pretty good thing. But you can work out the percentage difference. You can work out, like whether that is within the resolution of the experimental uncertainty. So, for example, you can work out the uncertainty of the voltage reading because it's plus or minus 0.01 volts. okay, and work out what that is as a percentage uncertainty of the smallest reading, so 0.01 over 1.43 times by 100% to work out what that percentage uncertainty is. Maybe you can, for lambda here, that lambda on the LED will have an uncertainty of some sort, say plus or minus 0.05 nanometers. And again, you can work that out as an uncertainty of, say, the smallest reading. I would go with that one. And then you can add these uncertainties together. All right, this is just doing it not by doing lines of worst fit, but just looking at uncertainties, add those uncertainties up, and then just see if your percentage difference lies within that uncertainty to say whether the experiment was accurate or not. I just left it as the right order of magnitude. Okay, now if you want further information, go to https://carlum.com for further resources. I think we've done pretty well there to go over 5 experiments. Experiment 16, determining Planck's constant. Experiment 10, the internal resistance of a cell. The variation of the resistance with temperature of a wire. The resistivity of a wire. And the current voltage characteristics of a bulb and a wire. Okay, thank you for listening in, and I hope that this has been useful to you, and goodbye until again.